Hello, everyone. How are you all today? Does anyone want to talk about the midterm before we get started? Hello, hello, Aaron. Hello, Rylan. So do you guys want to have a few words about the midterm before we get started, or nah? It was no biggie, I suppose, for some of you, but it may have been a bit of a concern for others. Let me just share my screen with you all. Okay. There we are. Done. Just have another window here on the side. So for the midterm, we weren't really trying to make it difficult. We thought it would be actually rather easy for most of you, since essentially only question 1 was new. Every other problem on the midterm either was covered in lecture, or you've already seen it somewhere, like in the cheat sheet or abridged notes or a theorem list or something, or exercises or homeworks. So there was nothing new, and we did try to put a lot of hints and suggestions throughout. So we were hoping that it wasn't hard for most of you. And what people asked seemed to be more technical questions. So hopefully it wasn't too difficult. What we seemed to get from it was that you were not as comfortable with relations as we thought you might be. So we thought you might be all comfortable with relations a bit more than we initially thought. Apparently I'm looking to the wrong camera. Let me change that. Sorry. There we go. So sorry about that. So it seems that some of you are saying that the last proof was a bit difficult. Yeah. So and again, to be clear, you've already seen it in lecture. So if you go back in lecture, I'm not going to say which one because there's still a makeup midterm to happen. But yeah, essentially only question 1 was new, and not really. It was just kind of nesting via sequences, so nothing really new. So I think what really got people is just the amount of terminology, not being comfortable enough with working through sets. So we kind of just essentially jumped over sets to get to relations. So we're gonna, even though on Friday we said we're gonna go to counting and combinatorics, chapter 16 of LADAM, I think it's only prudent to stick around with sets for a little while and relations. So we'll talk about counting, but we'll also interleave it with relations, just to reinforce that, because I'm afraid otherwise it would have been a waste of time. So that's the plan right now. We really were trying to make it like a fun midterm before the exam. Talk among the instructional staff was, this might be too easy and we're not really testing you on anything because all the problems were stuff you've already seen. But clearly that wasn't the case, like being under pressure and so that was clearly not the case. Many of you were clearly tested, and we have insight now about how to move forward, how to move proceeding forward. So that's good. So yeah, the topics covered in this class, they will be built up. You will build upon them in the next term in 2FA3. So I just want to let you know about that. Yeah, so I agree with you that the time pressure was a bit difficult. So that's why we're gonna try to slow down again. We clearly didn't slow down enough. So us and the other class will try to slow down again, and we're going to repeat some stuff you've already seen just to reinforce it, right? To really make sure you learn it. But we'll also go into a new territory like combinatorics, while again reinforcing stuff you've already seen. Okay, so we're going to try to make sure that everyone is at least comfortable for the exam. So we're gonna move a little bit, but also reinforce. Move a little bit, but also reinforce. So that way, for the students who are comfortable, they're still learning. For those who are not, there's a reinforcement happening. I'm not sure about the due date. I think it might be the 30th, but don't quote me on that. We'll look at it. I'm glad you guys enjoyed the different versions. I thought it would be fun. Yeah. So I think it might be useful to get out one more assignment just to, give people extra opportunity to do well when they didn't before. So we might have another assignment. Not yet so sure. We'll see how this going forward but reinforcing approach works. We might be able to, we might not. Maybe making a bonus is a good idea. So we shall see. Let me see if I have an image already for you. I have some images there. Okay. Oh, wrong image. Sorry, I thought I had some graphs available to show you. We'll see whether there's an exam prep booklet or not. So let's get started today, and we'll see how far we get. Hopefully far enough, but we'll find out. Let's see if I can show you some nice little graphs. Let's just do 4. 4 sounds reasonable. Okay. So hopefully we'll while I'm talking today, I'll show you guys some graphs and we'll see how that works out. The graphs will be related to this box, so hopefully not too difficult. If you are still not comfortable with what these words mean, please ask. Please make use of course help. It is important to know what these words mean, not just for this class, but really going forward. Univalent is really univalent and total are the most important to know. Did you write a total program, or does your program crash? All right. So total is like terminating, and univalent is your program going to spit out different answers depending on different times of the day, or is it completely determined by its input, right? So univalent is sometimes determinate or deterministic or partial function. Okay, so these are really important to know. So let me open up some images here for you. Yeah. Let's look at this one. So that's fine. So here's an image. If it's not big enough, please let me know. Try to make it bigger. Okay. Here. Okay. Let me know if you want me to make these things ever bigger. Always happy to. So let's just talk about this really briefly, since this is, I think, an issue for a few students. So what does univalent mean? All right. Univalent means for every input B and any possible output C, there's at most one output C. There's at most one output C. All right. So again, you had access to this cheat sheet for the midterm, and if you look at the cheat sheet, so the answer was right here on the cheat sheet. All right. So what does it mean to be univalent? It means in a graph, every node has at most one outgoing edge. Okay. Someone says, can I make the graph slightly bigger? Apparently I cannot, so let me try over here. Not here. Here. Let me go right there. Oh. No. No. Let's pull this one out. Get rid of this one. Okay. So here's a silly little graph. So let's just have a quick poll. How many nodes are in the graph? Who knows how many nodes there are in the graph? No, that's all right. We got it, Eamon. It works. So how many nodes are on the graph? There are 5 nodes. Excellent, right? 1, 2, 3, 4, 5. How many edges are in the graph? Who knows how many edges are in the graph? Excellent. There is 1, 2, 3 edges. Excellent. Is there an edge from 4 to 0? Does anybody know? Is there an edge from 4 to 0? I like how everyone's participating. This is great. No, exactly. The edge starts at 4 and then it goes down. The edge starts at 0 and it goes down to 4. The arrows matter. Excellent. Fantastic. All right. How many self loops are there? Exactly. 1 self loop right here. 4 goes to 4. Excellent. So is this a reflexive graph? A reflexive graph means there's a self loop to every node, right? That is, everything is related to itself. Is this graph reflexive? Excellent. No, because 1 doesn't go to itself. 1 doesn't go anywhere. 1 is forever alone, super isolated. Okay. So is this a total graph, right? Total means for every outgoing edge, there is an edge going into it. For every C, for every B, there's a C that it goes to. So total means there's every node goes somewhere. Right? Is this total? No, because again, 1 doesn't go anywhere, right? 2 doesn't go anywhere. Okay. So let's look at a different graph. All right. So here's a different graph. Okay. Is this graph total? Does every node go somewhere? Luis, yes, that's a good idea. That's why we already have this down here, Luis, on how to read them. So we've already done this last week on how to read these things. That's fantastic. This is not total. This graph right here is not total because 3 doesn't go anywhere, right? 0 also doesn't go anywhere. So it's not total because of these 2 reasons. Okay. Now, is this graph surjective? All right. Does anyone know if it's surjective? All right. Surjective means every node is reachable. Right? Every node can be reached from some other node. Yes, Luis, that's a good idea. No, because there is no way to get to 0. 0 is forever alone. Okay. So I hope this little quick adventure has been helpful. So let's return to the slides, and we'll come back to the graph in time. Okay. So just quickly, so these slides we just covered while talking about them, so I'll skip them over. Okay. So on Friday, I tried to talk to you about the Z-ISO standard. So one of the things you can take away from this class, among many others, is that you'll be able to say, hey, I'm familiar with some parts of the Z-ISO standard, which is useful to know if you're a computer scientist, right? Being familiar with the Z-ISO standard means you know about formal methods, right? And that can open some doorways for you. Okay, so that's that. So I thought it's important for you to know about this. So many of you have seen the single arrow before for functions. Some of you might have seen the arrow with a cross for partial functions. And if you stick around in computing or in math long enough, you might see the other possible arrows. And these are defined formally in the Z ISO standard. But in informal mathematics and computer science, the first two are very popular. The third one is also very popular, and so is the fourth one. And then you end up putting them together. So really, they're very quite popular. Some people don't want to use a lot of notation, and they'll just write words out. They'll write FORALL. Other people write an upside down A. So it depends on where you end up going. But they're quite nifty notations. And you notice you put one arrow on top of the other to get a new one. So here's a total arrow, right? Here's an arrow that's a total and an injection, okay? And then here's a surjection. And then if you take this one and that one and put them together, you get this one, right? Putting drawings on top of drawings. Yes, amen. They do look a bit weird, but having a compact notation can make things easier, right? Can you imagine if you had to work with numbers by writing them out? You know, like 123 would be 123. Can you imagine working with that long English sentence? It would be easier to just work with 1, 2, 3, 123, right? So depending on what you're doing, using exotic notation is very helpful. Some programming languages have a lot of exotic notation. So I recommend looking into J or looking into APL. These are fun languages. APL is a Turing Award was based on APL. So APL stands for another programming language. So anyhow, I just want to show you these, and hopefully today we'll look a bit more on some of these arrows, and we'll look more about some of this notation, just to get you at least a bit exposed to it, even if superficially, you know. So that way, going in the future, I'm like, I remember this has something to do with that standard from that class. Let me look it up. At least being aware of these things can be helpful. Okay. So you have these calc check input schemes as before, and I won't dwell on them. Some of these you've essentially proven in assignment 4 or homework 18, so that's pretty neat stuff. We talked about counting before, so let's return to that briefly, and then we'll get to the diagram and how that relates there. Okay, so we said before that the size of a product is the product of sizes. Okay, this one down here, where am I looking? This is the number of, this one right here, the number of injections is known as permutations. And then this one right here, how many subsets of B of size A are there? Does anyone know what this one is? This is the combinations, right? So we'll get to these. But now that we have the set notation, the arrow notation, we can actually talk about these things formally. Okay. So we're on chapter 16, but we're going to continue stepping back to relations just to make sure everyone's comfortable. And for those of you who are comfortable, just extra practice. And so hopefully not a big issue. So we talked about the slide last time, and maybe we'll release a homework on some of this stuff, perhaps in the guise of probability theory, just very super basic stuff. One thing I'd like to point out is right here, we're saying if there's a relation between A and B, and this funky arrow, the back part means it's injective, and then the front part means it's surjective, and because there's no line cutting the arrow, this is total. So if there's a total surjective bijection, because there's no arrow, it's univalent. So we have a bijective mapping. It has all the 4 properties we're interested in. It's total, it's univalent, it's surjective, it's injective. That means it's a mapping and it's a bijection, which together means it's an isomorphism. A mapping, bijective mapping is also known as an isomorphism or an iso, right? Iso means same, morphism means shape, right? So essentially what this says is if there's a way to change A and B, like there's a non-lossy protocol between A and B, I can pair them up, then really, if I can pair them up, there must be the same amount of things between A and B. Okay, so some nice stuff. You've all gotten very quiet, so I'm very concerned. Does that mean I should go faster or slower? Please let me know. Is anyone there? All right. Okay. All right. I just want to make sure I don't want to lose anyone. That's the last thing I want to do. I don't want to lose any of you. So please let me know. Okay. So I think it was week 4. We talked about permutations. We defined them inductively. And we said, hey, you know what? 0 factorial, n factorial. So if your parents walked in and they saw you writing 4 factorial, they might say, why is the number 4 screaming? What's going on, right? So that's what we did a while ago, right? We just gave you an inductive definition. We said, hey, believe me that this is the number of bijective mappings, right? We said it's the number of ways to arrange n many people in a line. That is to say, it's the number of bijective mappings between fin n and the number of people, right? So this is right here. So we tried to get you to, we just said believe me a few times, and we tried to convince you. But now that we have set theory, we have quantifiers, we can actually prove these things and then formalize them. Okay. That's fantastic. All right, that's a good way to go, and I'm happy to continue doing so. So here we're saying. So in this slide in particular, we're saying let fin n be the first natural numbers. Okay, so fin 1 has the first natural number, which is 0. Fin 2 has the first 2 natural numbers, which is 0 and 1. Okay, so in general, fin n has n natural numbers. Okay, now remember this funky arrow, right? It's an arrow, so that means it's total and univalent because there's no bar. Total and univalent means for every input, there's exactly 1 output, okay? And this curvy angle at the back means it's injective. So this is total, univalent, injective. That means different things go to different outputs, and everything has a unique output, okay? So we're saying, given any number from 0 to r minus 1, I'm going to give you exactly 1 number from 0 to n minus 1, and different numbers will go to different numbers. Okay, so another way to say that is to say I have r numbers, and I have n numbers up there, and I'm gonna take my r numbers and I'm gonna stick, you know, each one of them is gonna point up somewhere, and every number points up to exactly 1 place, and different numbers don't point to the same thing. Okay, so just as here we have a bunch of numbers and they're pointing to each other, so you can think of it like that. And this idea is I have n numbers up here, r numbers down here, and whenever I take one and I point it up somewhere, I can essentially take that number and stick it up there. And so what I'm really saying is I have n people, and I'm going to arrange r of them, right? The numbers 0, 1, 2, 3, 4, 5, 6, all the way up to n minus 1. And then I'm going to take the r possible slots and assign them to the people to get a permutation of it. Okay, so I have n people, I have r chairs, and I'm going to give some of my r chairs to the n people, to some of the n people. So some people will be able to sit, some people will not. Okay, and so I'll have different arrangements of people sitting and not sitting. All right. I feel like I'm beating the horse, but please let me know. And so this is just the number of permutations from week 4, homework 4, I think it was, 4.2, or was it week 6? I'll look it up. Okay. And then again, we're still following the book, right? So we talked about bags very briefly. We said a set doesn't care about order. A sequence cares about order. A set doesn't care about order, but a set also doesn't care about multiplicity. All right. Whereas a bag is like a set, and like a sequence, it's somewhere in the middle. A bag doesn't care about order, but a bag cares about multiplicity, right? So maybe we'll talk more about bags tomorrow, but for now I just wanted to mention what a bag is, all right? Just to put this under sound footing, and you can see it in the book if you're so inclined. Okie dokes. Please continue asking questions. All right? Make sure I see you on all these channels. So a few slides ago, I showed you this one, right? The number of sets S that are subsets of B and of size A. This is known as combinations, right? For every set S, I can choose if S has an element or doesn't have an element. So I can always make a choice. And I have B many possible choices. So I'm going to make B choose A many combinations, okay? So we saw choose as well back in homework 4. And again, now that we have quantifiers, we can look at new theorems. We can try to prove them. CalcCheck has division, right? So we can try to rephrase them using rationals and division, right? So we might release another homework, but hopefully you remember some of these from week 4. But not to worry, we'll introduce them maybe in an exercise later this week to get you familiar with it. So if you think of B choose A to mean I have a set of size B and I want to pick A many things from it, right? So I'm going to go to the restaurant, and at the restaurant they have B many dishes, and I want to pick only A many of them, okay? So if there's N many dishes and I'm going to pick 0, how many ways can I pick 0 dishes? There's only one way to pick 0 dishes. If I'm at the restaurant and the restaurant has N many dishes and I'm going to pick 1 dish, how many ways can I pick that 1 dish? Well, there's N dishes. I just point at one of them, or point at another, or point at another. So as many possible ways I can point. So there's N many ways, okay? If there's N dishes and I want all of them, how do I ask for all of them? If I say, give me all, right? And we're good to go. So this is informal, and we'll try to do some formal calculation in the exercises and maybe a bit more tomorrow, okay? Just a quick question. Who's not familiar with combinations? So maybe you haven't seen them in grade 11 or grade 12 or first year. Just curious. So everyone is familiar with combinations? We can just test you on it tomorrow? All right, I just want to make sure that they're new at least to somebody. All right, thank you. So there's this thing called Pascal's Triangle, right? And it's a way to compute these combinations. In particular, this 1618 rule is sometimes called Pascal's Triangle. It says to get the formula for n choose R, go to the previous row to the right and the previous row to the left. So if I want 4 choose 2, I just add up the ones right above it. 3 choose 1 plus 3 choose 2 is the sum of 4 choose 2. Okay, so it's a nice little formula, right? And then I find out that it's just 6, right? So if I have 4 items and I try to choose 2 somehow, it ends up being 6, all right? This one is a bit familiar. Maybe you've seen it before. We said n choose R is the number of sets of size R from a set of size n, right? But then when you add up all possible sets of size R of a subset of size n, you're really saying I want the number of all the subsets. But the number of all subsets is 2 to the n, right? So that's some neato stuff. Let me just go here for a sec. I think I've put some more examples for you up here. Let me just check if I do or if I haven't updated this. So combinatorics. So here's a few calculations and some other examples to get you comfortable. I won't cover them in class. If you're comfortable with Haskell, you can run a few Haskell programs. We might get you to do something like this in later this week or next week. So we'll see. And some of these examples I said about these choices I've tried to explain down here as well. So we'll see how many of them we get to in class and versus how many we don't. So we'll see how that goes. Yeah. Okay. Are there any questions here? Okie dokes. So let's go back here. All right. So I'd like to get back to relations, but these choose or choice functions, right? N choose k are sometimes called binomial coefficients, right? And for the reason for that is because of this number, this theorem known as the binomial theorem, which essentially says it lets you know how to make choices between two things, x and y. So if you're adding x and y and you want to make n possible choices, what it's saying is you can pick n minus k x's and the rest are all y's, right? And then you have to pick the k's somehow, right? And because multiplication order doesn't matter, it's just n choose k, right? So and this number pops up frequently when you get to probability. So for those of you who are going to be doing some advanced computing, maybe third year, fourth year, or advanced math, statistics, you'll likely run into the binomial theorem repeatedly. It's a very handy dandy result. The left-hand side is multiplying x times y n times, okay? And so we're really going to have to distribute a number of times, and then we're going to collect like terms, right? There's going to be k many y's, and the rest are all x's. How many x's are there? Well, I'll sum up over the possibilities, right? So here, when we just write n, we were talking about fin n, right? The set of the first n natural numbers. So you run into fin n almost all the time. Fin n is almost always there. When you talk about a for loop and your for loop runs n times, you're talking about fin n, right? When you tell someone to do something n times, when you take a number to the power of n, you're really working with fin n in some sense, right? Every number n is the size of fin n, right? So numbers are sets when you use the hashtag operation to get their size, okay? So there's some philosophy about how really, as people, we think in terms of sets, but we try to pretend we work with numbers, right? Like, what is 3? What does 3 mean? I don't know. Like, how do you tell someone what 3 means, right? If you're pedantic, you might say, oh, 3 is the successor of the successor of the successor of 0. Okay, what does that mean? Right. So some people say, oh, 3 is this vague concept. Instead, we talk about sets, and these sets are isomorphic. So there's a bijective mapping between them. I can pair them up, okay? And the sets of size 3, all of these sets is the idea of 3. Okay, so number 3 is captured by looking at all possible collections of size 3. Okay, that's very hippy dippy. Take your philosophy as you like. Should we be able to? Yeah, you can take my word for it. If I ask you to prove it, I'll give you hints. In particular, n is a natural number, so take n to be 0, then take n to be non-zero. So induction. So for extra practice, you could try working with this through induction. That would be a good extra practice to try to do. Okay. So I'd like to get back to relations. So that whole going forward, stepping back, going forward, stepping back. So just really want to make sure people are comfortable. Don't want to. So we talked about a bit counting. I want to go back to relations. We'll come back to counting. Just really want to make sure that you didn't waste time learning about relations and then you forgot. You really need them going forward, because a relation is a graph, and computer science graphs are like the bread and butter of computer science. So you really need to know what a graph, what a relation is. So let's have another quick game, since people really enjoyed that. Oh, there's no 5. Try 4. Okay, so here's a quick little game. Amen. People will ask you what 3 means. What does red mean? What are words, right? What does and mean? What does it mean for things to mean? So philosophy is fun, but what does it mean? And other things you can waste your life with. So here's a quick graph. Let's do as we did earlier. It's too early for this. I'm glad you're enjoying. So who thinks this graph is reflexive? Right? Everything is related to itself. Who thinks this graph is reflexive? You have 5 seconds. 5, 4, 3, 2, 1. Good job to everyone who answered. It's not reflexive because, for example, there's no self loop for 3. 3 is not related to itself. Okay, so for those of you who are not participating, please do participate, because this is a very quick way for you to know if you know something or not. And even if you're not going to reply, just breathe to yourself no or yes, and then check your understanding, right? Then you'll know if, hey, I don't really know this concept and I should seek more help, or I do know this and maybe I should focus on learning this other thing. Okay, so please check your understanding. So is this an irreflexive graph? Right, 5, 4, 3, 2, 1. It is not an irreflexive graph. Irreflexive graph says for every b, it's not the case that b is related to b. But wait, 2 is related to itself. So this is not irreflexive. Irreflexive means no self loops. Okay. Is it a symmetric graph? Does anybody know? 5, 4, 3, 2, 1. Somebody's learning. Good, good. Please let me know when you're learning. Good to know. So symmetric means if there's an arrow going this way, then there's an arrow going backwards as well. All right. So there's an arrow from 2 to 3, but there's no arrow from 3 to 2. So it's not symmetric. Is it an anti-symmetric graph? All right. Does anybody know? There's some hints down here. Is it an anti-symmetric graph? All right. 5, 4, 3, 2, 1. So anti-symmetric, just right here, right, says if there's an arrow between the two things, they have to be the same. All right. So in this case, that means related nodes have to be self loops, and in this case, yeah, there's only self loops. Whenever there's an arrow going both ways, it's a loop. So here's an arrow from 2 to 2, and then there's an arrow from, well, 2 to 2, and that arrow is a self loop. Likewise, from 4 to 4, self loop, and there's no arrow going backwards, none backwards, none backwards. So we're good. All mutual arrows are necessarily self loops. Mutual, self loops. Good job. Yeah, I like there was a lot of question marks there. So it's good we're trying this, right? And you know where you're having some trouble. Is this graph asymmetric? Right. So asymmetric means there's at most one edge between any two pair. Right. For any two pair BC, if there's an edge between BC, then there can't be an edge the other way around. There's at most one edge. Right. So that's a good question, Aaron. Let's ask. 5, 4, 3, 2, 1. Lots of hesitation, I'm saying. So it says for any BC. So in particular, if I take C to be the same as B, then it says BB, B is related to B, means it's not the case that B is related to B. So if you have asymmetric, you can't have any loops. So here's a loop, and here's a loop. So nope, this is not asymmetric. Okay. Nito petito. Alrighty then. Last one, transitive. Is it a transitive graph? All right. So transitive means for any two-step path can be reduced to a one-step path. Right. If I have a long path, I can always squeeze it down. Is it a transitive? No, it's not, because I can go from 2 to 4 in one step, and then I can go from 4 to 1. That means I can go from 2 to 1. That's fantastic. This and down here got squeezed into one path. That's fantastic. But what about if I go from 2 to 4 and then from 4 to 0? There's no way to go from 2 to 0, right? So it's not transitive. Good job. Alrighty. So I hope some of you had fun doing that. So we talked about these abstract proofs, right? We said, hey, we have this square less than or equal to, this O plus, this square less than or equal to, right? And then at one point, O plus became a fat semicolon, right? And we said, hey, do these for the assignments. They're just super fun time stuff, right? Instead of having to prove it for less than or equal to, for implies, for divides, we said it's just an order. Square less than or equal to is just an order that stands in for the other notations, right? So back here in assignment 2, we said, let's just use square less than or equal to. And then we proved a bunch of properties about square less than or equal to. Right? This abstract reasoning, sometimes for the rest of the class, we'll refer to it as relational reasoning because we're talking about relations. Just means we're not talking about, we're not using quantifiers anymore. So here's a proof that if two things are reflexive, then their intersection is reflexive. Okay, so let's stop and pause back for a minute. Two relations are reflexive means the graph R has loops everywhere, and the graph S has loops everywhere. And then when I take the intersection, I'm saying, let me look at the common subgraph that belongs to R and belongs to S. Now, since R has self-loops everywhere, and S has self-loops everywhere, and the intersection is a common part, the intersection should obviously have self-loops everywhere. And that's what this theorem proves. Now, if we try to prove it using this for all, right? For all B is related to B, the proof will suddenly get long. Okay, so in assignments 1, 2, 3, and 4, in the 4 assignments, we never let you use quantifiers because early on you didn't even know about quantifiers, right? But now that we're talking about relations, you can express an inclusion. You can express an inclusion using, for all. You can express intersection using set theory. You can express equality using another for all. So these can get really, really long. And we just want to remind you, just because you have access to these variants does not mean you want to do it this way. It can get really, really long and wide. So especially in the midterms and exams and things, when you're short on time, this approach is not your friend. Brute force, not your friend, okay? So it can be really easy to just do it this way, as you have done in assignments 1, 2, 3, and 4. So just want to remind you. Okay, ducks? What would idempotency look like graphically? So I'll leave that to you, Eamon. Maybe you'll read down here. Maybe you'll read down here. Okay, so I'll leave that to you. Fun stuff. Okay. So here's a few more properties. Maybe we can talk about them a little bit more. So one of the things that I think some people have a bit of trouble with is when we talk about monotonicity. So we had monotonicity of and, monotonicity of or, and of course union is just like or, and so it's important to remember you can use monotonicity results there. Okay, so if you assume two relations R and S are this time irreflexive, so irreflexive means if you look at the graph, there is not a single self loop in R, and there's no self loops in S, then when I stick them together, I just put them beside each other. There's no self loops here, no self loops here, so together there's still no self loops. That sounds obvious, and we can prove it this way. We say, all right, here's them stuck together, and when I stick them with the identity, so I just focus down on the self loops, Are there any? Well, we know that and distributes over or, as always, right? So I can distribute identity and R or identity and S. So even though it's union and intersection, you can still think of these as and or because they satisfy the same interface that we talked about a while back. They both satisfy this so-called distributive lattice interface. Okay, ducks. So if you think of them as and or, you remember you can distribute, and now you say, wait a minute, irreflexive meant this thing is equal to R, right? But if you used the another form where it's contained in, you would have to use monotonicity, right? So this one would be contained in 0. This one would be contained in 0, right? So the empty set, you can think of it as 0 or as false, right? And then 0 union 0 or false union false is just the same thing, okay? So when you do the proofs for relations, not by using for alls and quantifiers, life can get very easy, and then they become calculational proofs that you've already done since assignment 1. So I just really want to hammer that home. Just because relations are sets of pairs doesn't mean you need to work with them that way. Working with them that way can be very tiring and exhausting. So I just want to point that out. Okay, so here's a few more operations I just want to mention. I'll talk about them tomorrow. So I'll show them here on the slide. Maybe I'll talk about them tomorrow. This is more from the Z ISO standard, right? And you will definitely see these in the future using different notation because some people don't subscribe to the Z ISO standard. But for today, I just want to wrap off with letting you know that course evaluations are out. I would really appreciate it if you evaluated what you thought of the course, how it started out, how it's changed, how it's going. I'd appreciate if you gave me some constructive feedback on what you liked that I did, or what you would like me to stop. This is Discrete Math 1. In a month or so, you'll be starting Discrete Math 2. And if you thought, hey, this Musa guy was great, and I would like to have him teach for me next term, if you fill out those forms, maybe I can get the job and I can teach you next term. If you thought I wasn't great, you should say so, and then I won't teach you next term. So I would appreciate it if you did the course evaluations. It looks like we have 2 minutes still, so maybe we'll talk a little bit about domain and range. So the domain restriction says you have a relation R, and you want to restrict it to a set A. So let's do a quick problem right now. Here's our graph, and I want to zoom down to the graph consisting only of 2, 3, and 1. That would be this graph. Okay, so I threw away the other part. That's what domain restriction is. Okay. Anti-restriction means I want to zoom down to everything not in A. Okay. Range restriction says I want to zoom down where the outgoing edges are in B. So for example, I want to zoom down only to where the outgoing arrows are in 4 and 0. So here's an outgoing edge in 4 and 0. Right. So that's where I would land. All right. So you'll see these sometimes written in the form in other places. You might see them like this: f for a function f, and then people will write f of a for a set A, and they'll call it the direct image instead of range restriction. So you'll see these things again. Anyhow, we've run out of time, so perhaps we'll pick up from here tomorrow. I'd appreciate it if you did the course evaluations. I'm here if you have any questions, and I wish you all the best. Bye-bye, everyone.